channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with your physics, that what we'll have to discuss here in the detail about it. So in terms of physics, here um, we had done your unit 1, which is your physical world, unit 2, that is units and measurement, and this is unit 3, which is your motion in a straight line. This is your unit 3rd. We had done your unit 2 in this has been, as I told you, physics 11th class, and that is of course been important one, so you have to go for it. Now in terms of it, we'll start with this, but before starting with this, we had left some of the questions related to units and measurement, so that what we'll have to discuss here. So we go for the first for those, and then we'll be continuing with the motion in a straight line. So as I told you, the questions, 14 questions and more, that what we have solved in the last class. The 15th question we have here is that a famous relation in physics relates moving mass m to the rest mass m naught of a particle in terms of its speed v and the speed of light c. This relation first arose in the consequences of a special relativity due to the Albert Einstein. A boy recalls the relatives along correctly but forgets where to put the constant c. He writes m equals to m naught by 1 minus v square whole half. Now the 16th question, you have to guess where to put the missing c here. And now the 16th question, what it arises, the unit of the length convenient for an atomic scale is known as an angstrom, and it is denoted by a angstrom, that is 1 angstrom is equals to 10 to the power minus 10 meter. The size of the hydrogen atom is put 0.5 angstrom. What is the total atomic volume in a meter cube of a mole of hydrogen atoms? Here 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liter, that is molar volume. What is the ratio of the molar volume to the atomic volume of a mole of hydrogen? You have to take the size of the hydrogen molecule to be about 1 angstrom. Why is this ratio so large? Now we go for the 17th question be done. Now we talk about the 18th question, that is the explain the common conversation clearly. If you look out the window of a fast moving train, the nearby trees, houses, etc., that seem to be more rapidly in a direction that is opposite to the train motion, but the distant object, hilltop and the moon and the stars, etc., seem to be stationary. In fact, since you are aware that you are moving, these distant objects seem to move with you. Where we talk about for the another 19th question, that the principle of the parallax in this is used to determinations of the distances of very distant stars. The baseline AB is the line joining the earth, that two locations that are months apart in its orbit around the sun. That is, the baseline is about the diameter of the earth orbit, which is equals to 3 into 10 to the power 11 meter here. And however, even the nearest stars are so distant, and that are so wherein that the parsec is a convenient unit, where that is a convenient unit of the length or an astronomical scale, and it is the distance of an object that will show a parallax of 1 second of arc from opposite end to the baseline, that is equals to the distance from the earth to the sun. And how much is the parallax in the terms of meters here? Now talking about the 20th question that we have to discuss here, which is the nearest star to our solar system is 4.29 light years away. How much is this distance in terms of parsecs? How much parallax would this star instead Alpha Centauri, where that shows when viewed from the two locations of the Earth 6 months apart in the orbit around the Sun. 21st question we'll talk about for units and measurement is, to be precise, measurement of the physical quantity that are need of science. For example, in ascertain the speed of the aircraft, one must have to accurate method in to find the positions at closely separated instants of time. This was the actual motivation behind the discovery of the radar in World War II. Think that of different examples in the modern science where that precise measurements of length, time, mass, etc. that are needed. Also, whenever you can give your quantitative ideas and of the precision method as well that be needed. Now we talk about for the another question has been 22th question. Just as precise measurement that are necessary in science, it is equally important to be able to make the rough estimates of the quantities that using the rudimentary ideas and the common observation. Think of ways by which you can estimate the following. Where an estimate is difficult to obtain, try to get an upper bound on the quantity. That the total mass of the rain bearing clouds over India during the monsoon, the mass of an elephant, the wind speed during a storm, the number of the strands of hair on your head, the number of the air molecules in your classroom. The 23rd question that we will discuss here is, the sun in the hot plasma, that ionized matter with its inner core at the temperature exceeding 10 to the power 7 Kelvin and its outer surface of the temperature of about 6000 Kelvin. At these high expect of the mass density of the sun that to be in the range of density of solids and sun 2 equals to 2.0 into 10 to the power 30 kg, where the radius of the sun is 7.0 10 to the power 8 meter. We will talk about the 24th question here, that will be, when the planet Jupiter is at the distance of 824.7 million kilometers from the Earth, its angular diameter is measured to be 35.72 degree of arc, and that calculate the distance of the Jupiter. Now we have an additional questions here that you have to find it out and you have to do that. In the same way, a man walking briskly in rain with a speed v must slant his umbrella forward, making an angle of theta with the vertical, and a student derives the following relation between theta and b, where tan theta equals to v, and checks that the relation has a correct limit as b tends to 0 and theta tends to 0 as expected. We are assuming there is no strong wind and that the rain falls vertically for the stationary man. Do you think that this relation can be correct? If not, you have to guess the correct relation. 26th question we'll talk about it, which is being, it is that is claimed that two cesium clock, if allowed to run for 100 years, that is front from any disturbance, may differ by only about 0.02 seconds. What does the imply for the accuracy of the standard cesium clock in measuring a time interval of 1 second? Another is to estimate the average mass density of a sodium atom, that assuming its size to be about 2.5 Armstrong, you have to use the known values of Avogadro number and that atomic mass of sodium. You have to compare it with the density of the sodium in its crystalline phase, where 970 kg meter cube, and are the two densities of the same order of magnitude? If so, why? You have your another question has been that the unit of length comment on the nuclear scale in the forms 1 of, that is forms equal Fermi equals to 10 to the power minus 15 meter, where nucleus sizes obeys roughly the following imperial relation, which is r equals to r naught a 1 by 8, 1 by 3. So where r is the radius of the nucleus and a is the mass of that r naught, and r naught is a constant equals to about 1.2 Fermi, and show that the rule implies that the nuclear mass density is nearly a constant for the different nuclei. Estimate the mass density of the sodium nucleus. You have to compare it with the average mass density of a sodium atom that is obtained in this. That's what we'll have to discuss about it. Now we go for another one, which is being the 29th question of the sessions here, and that is that is within the 29th question. And the question we have here is: a laser is a source of very intense monochromatic and unidirectional beam of light. These properties of a larger light that can be exploited to measure long distances. The distance of the moon from the earth has been already determined very precisely using a laser as a source of light. A laser light beam at the moon that take 2.56 second here to 2.56 second to return after reflection. Now we'll talk about for the another one, that is being the another question is the 30th question, and but before that to return the reflections of the moon's surfaces, and how much is the radius of the lunar orbit around the earth. Now coming towards this another question has been the 30th question. We'll talk about it, and that the question we have here, which is a sonar, that is your sound navigations and ranging, uses an ultrasonic waves to detect to locate object underwater. It is a submarine equipped with a sonar that the time delay between the generations of probe wave and receptions of the echo after reflection from the generations of probe waves and the receptions of echo after reflection from an enemy submarine is found to be 77.0 second. What is the distance of the enemy submarine? Speed of sound in what is 1450 the meter second inverse. Now 31st question is: the farthest object in our universe discovered by the modern astronomers are so distant that light emitted by them takes billions of years to reach the earth. These objects, known as quasars, have many puzzling features which have not yet been satisfactorily explained. What is the distance in kilometers of quasar from which light takes 3.0 billion years to reach us? The 32th question we have: it is well known fact that during a total solar eclipse that the disk of the moon almost completely covers the disk of the sun. From this fact, that from the information you can gather from examples that to determine the approximate diameters of the moon. Now a great physicist of the country, which is Pam Dirac, which is loved playing with numerical values of the fundamental constant of nature. This led him to interesting observation, which is Dirac found that from the basic constants of atomic physics, Ce, which is mass of electron and mass of proton, and the gravitational constant g, he could arrive at the number with the dimensions of the time. Further, it was very large number, its magnitude being close to the present estimate on the age of the universe, which is near about 15 million years. From the table of the fundamental constant of this book, you have to try this. If you can construct the number or any another interesting number that you can think of, it is coincidence with the age of the universe was significant. What would this imply for the consistency of the fundamental constant? Now we talk about for the chapter 3, which we'll have to discuss here in the detail about it. So we'll go for it. So motion in a straight line, what it states that what we'll be discussing here. Motion in a straight line. First of all, you have to know what is motion in a straight line is all about. That what we'll discuss here in the detail about first, and then we'll go for further to continue. In a motion in a straight line, motion is a common to every thing in the universe. We walk or run and ride a bicycle. Even when we are sleeping, that air moves into and out of our lungs and blood flows in arteries and veins. We see falling from the trees and water flowing from down a dam. Automobiles are planes carrying people from one place to the other. The earth rotates once every 24 hours and revolves around the sun once in a year. The sun itself in the motion is a Milky Way, which is again moving within the local group of the galaxies. Motion in a change is a change in positions of an object that with time. How does the position change with time? And in this chapter we shall learn how to describe motion. For this we develop the concept of velocity and acceleration. We shall confine ourselves to the study of the motions of object along a straight line, as also known as the rectilinear motion. So here we develop the concept of velocity and the illustration. We shall confine ourselves to study the motions of object along with straight line, that is also known as rectilinear motion as well. For the case of the rectilinear motion with uniform acceleration, a set of equations that have been obtained, and you have to finally understood that the relative nature of the motion. We introduce the concept of relative velocity as well. In our discussion, we shall treat the objects in motion as point object. This approximation valid so far as the size of the object is much smaller than the distance it moves in the reasonable durations of time. In a good number of situations in real life, the size of the object that can be neglected and they are be considered as point-like object without much error. In kinematics, we study the ways to describe the motions without going into the cause of motion. What cause motion describes in the chapter, and the next chapter forms a subject matters of, that we'll discuss in the next further chapter as well in a detail. So motion in a straight line, that has been cleared. Now we'll discuss about the position, path, length and displacement. So first what we discussed about it is your introduction. Now the second part we'll discuss here is position, path length, and displacement. So here we go. So in positions, path length and displacement, earlier you learned that the motion is a change in positions of an object with time. In order to specify the position, we need to use a reference point and a set of axes as well. And it is convenient. First we'll discuss about I told you the whole what we'll discuss in this chapter is been about introduction, position, path length and displacement, average velocity and the average speed, instantaneous velocity and the speed, acceleration, kinematics equation for the uniform accelerated motion, relative velocity. That what we'll have to discuss here. So yes, to fit then accordingly that it is convenient here to choose a rectangular coordinate system, that is consisting about the three mutually perpendicular axes, that is labeled x here. On the same way that the point of the interactions of these y and z axes, that is the three axes, that is called the origin and serves as a reference point. So the point of intersection, I just write it down for you also that you will be get to know about it in a detail here. So where there are many frame of references and many more to discuss about it, and accordingly you have to that is we'll have to discuss here in the about the detail as well. So yes, we go for it. With the same we that what will be path length and the displacement that we'll discuss here in the detail. And now we'll go for the first reference point, but before that we'll had discuss about the rectilinear motion and the kinematics. So we just on that describe that. So rectilinear motion, I will just tell you, the study of the motions of object along a straight line is also known as rectilinear motion. So first we go rectilinear motion. What is rectilinear motion? We just go for it. So rectilinear motion is the study of motion of object, the study of motion of objects along a straight line, also known as rectilinear motion. Now we talk about for kinematics. Kinematics, we study ways to describe the motion without going into the cause of motion. What cause of motion describes, that we'll discuss here. So that kinematics I will be clearing you. Now we talk about for that, as I told you, that is of further which is in terms of your reference point. So we go for reference point, just make it notes, because these were the subjects that you will have to know about it, and these were the points that you have to clear. Reference point. What is reference point? The point of interaction the point of intersection of these three axes which axis they are talking about, x, y and z axis, is called origin, which is denoted by O, and serves as the reference point. So reference point also the point of intersections of all the axes that serves as reference point. Okay, so now we talk about for the another one, that the coordinate x, y, z of the object that describe the positions of the object with respect to the coordinate system. You have to measure the time. We positions a clock in the system, and this coordinate system along with the clock constituents frame of reference here. Now in one or more coordinates of an object that change with time, we say that the object is in the motion. Otherwise the object is said to be in the rest with respect to the frame of reference here. On the same way, here that the choice of a set of axes in the frame of reference, that depends upon the situation. For example, like for describing the motions in one dimension, we need only the axis. To describe the motions in the 2 or 3 dimensions, we need the set of 2 or 3 axes here. Description of an event depends on the same frame of references that chosen for the description. And for example, when you say that the car is moving on a road, you are describing the car with respect to a frame of reference that attached to you and or to the ground, but with respect to the frame of reference attached with the person sitting in the car is at rest. On the same way, to describe the motions along a straight line, we can choose an axis, say x-axis, so that it coincides with the path of the object. We then measure the positions of the object with reference to the conveniently chosen origin, which is say 0 as shown. The position to the right of 0 are taken as positive and to the left of 0 as negative. And following these conventions of the position coordinate of P and Q, we'll discuss that plus 360 to 240 minus 240 plus 240 meter, and similarly the position of the coordinate of the R, that will discuss the minus 122, that is minus 120. So we'll go for this, and before that we'll talk about the path length here. So we go for the path length. First we'll discuss about path length. So the path length we have here in the same way, you have to consider the motions of a car along a straight line. We choose an axis such that it coincides with the path of the car's motions and the origin of the axis as a point from where the car started moving. That is the car where x is equals to 0 to t equals to 0 at t equals to 0, and let p, q, r represent the positions of the car at different instant of time. You have to consider the two cases of motion. In the first case, the car moves from 0 to p, then the distance moved by the car is OP, which is plus 360. We'll draw that. The distance is called that the path length here. So here that traverses the car here. In the second case, the car moves from 0 to P and then moves back to P to Q. You have, during this course of position, the path length traversed that OP plus PQ, that is in plus 60 plus 120, that is plus 480. So path length is a scalar quantity, and a quantity that is have magnitude and no radiation. So we'll go for the same path length. First we'll draw the diagram here. This is all about path length. X-axis origin and the positions of a car at a different times. This is minus 160. This is minus 120. This is on R. This is minus 80, minus 40, minus 20, minus 0. This, sorry, 0. No sign. This is origin. So then we have your 40, 80, 120, 160, then 200, 240, 280, then we have your 320, then we have your further 360, then we have further is your 400, and again we have your 440. So that which is on this is your plus side, that is plus x, and this is just my negative sign, that is your minus x here. From origin to the left side it will be your negative, on the right side it has been the positive here. So on the same way, these were the position at this is the origin, that at 240 it has been the q, and this has been the p at your 360. Okay. So accordingly it will be go for it. And for path length I will just describe the same. Total distance covered is known as path length. In the same way, that it is a scalar quantity that has magnitude only, no direction. Okay, for today's class it is that much. We'll be ending it up here only. We'll discuss the rest of the class in the next coming class. And before ending it up, it's a huge request to all the viewers to please go ahead with like, share and subscribe, so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Other than that, we are dealing with the chemistry. We had done your part 1 for class 11th chemistry, and part 2 we are dealing physics. Part 1 we are on third unit, that is motion in a straight line. We'll continue with the next, and we are dealing with the quantitative aptitude, where we had started with arithmetical ability. We had done 16th topic there. You can just go for it. And we had done your reasoning, which is your verbal reasoning we had completed, and with non-verbal reasoning we had completed. We are dealing with the DBMS, as well as we are dealing with your another one as well, which is your computer-based numerical and statistical technique. In terms of physics part 1, what we have to cover up is the physical world, which we had completed, which is what is physics, scope and excitement of physics, physics, technology and society, fundamental forces in nature, nature of the physical law. Unit 2, which we had completed, units and measurement, which is introduction, the international system of unit, measurement of length, measurement of mass, measurement of time, accuracy, precision and instrument with the errors in the measurement, significant figures, dimensions of physical quantity, dimensions formula and dimensional equation, dimensional analysis and its application. Unit 3rd, which we are in, that is motion in a straight line. We had completed the introduction, position, path, length and the displacement, and we will complete that, and then after that we'll complete it your averages, velocity and the average time, instantaneous velocity and the speed, acceleration, kinematics, equation for the uniformly accelerated motion and relative velocity. Then further we'll complete your unit 4, which is motion in a plane. Then we'll discuss the next is your unit 5, laws of motion, unit 6, work, energy and power, unit 7, system of particles and rotational motion, unit 8 is your gravitation. Then further we'll discuss the rest in the next coming class. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.